Great. Yesterday we worked with law of sines and area of triangles, calculate the area of triangle. Law of sines, once again, it's just another way of being able to calculate and manipulate through triangles that aren't right triangles. And that's basically what we're trying to do, is manipulate triangles that are not right triangles. You have your law of sines, you have your law of cosines. Calculate the area of the triangle by multiplying 1/2 product of two sides times sine of the angle included. So those are all things that we can use to manipulate for triangles that are not right triangles. If they're right triangles, they're easier to deal with. If they're not right triangles, then it's a little bit more difficult, but we can use law of sines and law of cosines to be able to manipulate around the triangles. Questions you have on any of the problems you had, 8 problems to do, or did we all opt into a family night last night and did the homework and did board games with their family? All right, we're going to continue onwards. I chuck on, but ultimately it's the effort and work that you put into this, and you're great. So I'm just a person that's there. I'm just a person that records. I'm just a person that records whatever your efforts are and whatever your work is. As people say teachers give grades, I don't give the grades. I just record the grades that you have efforted. So today we're going to look at, once again, law of sines and law of cosines, but we're going to work out what is called the ambiguous case. The ambiguous case. If we are given a triangle ABC, we have angle B is 50 degrees, we have little b is 7, and we have little c is 8. And we want to calculate little a. We want to calculate little a. Well, we can now use law of sines and law of cosines and manipulate around any triangles. Law of cosines, it's a little bit more difficult, a little bit more of a challenge to work with. Law of sines is a little bit easier to work with because you're looking at the law of sines as the ratio of sine of an angle to the length of the side opposite. They will be in proportion. That's a little bit easier to work with. That's what we worked on yesterday. So if we would take a look, we want to solve for little a. Well, to solve for little a, we need to know angle A. Well, we don't know angle A, so that's going to be a secondary thing or initial thing that we need to be able to calculate is angle A. Because with angle A, we can use law of sines or law of cosines to be able to find little a. But I don't know angle A. We need to work on that. But what I do know is I know angle B, we know little b, and we know little c. So if we set up our law of sines equations, we have the sine of angle A over little a equals the sine of angle B over little b, which equals sine of angle C over little c. Our law of sines equations that we worked on and developed yesterday. And if we evaluate what we have within our triangle, we have little b and we have little c. And we know angle B. So we know little b, we know little c, and we know angle B. So within our law of sines equations, we know 3 of 4 elements to a proportion. If I know 3 of 4 elements of the proportion, we can solve for that 4th element of the proportion. So subbing in our values here, we have the sine of angle B, which we know is 50, over little b, which is a value of 7, is equal to sine of angle C. Well, we don't know angle C, but we know little c is a value of 8. So once again, we know 3 of the 4. So we can use our mathematical skills that we learned in 5th and 6th grade, how to solve a proportion by cross multiplying and dividing. Well, if we diagonally multiply, we have 8 sine of 50 degrees is equal to 7 times the sine of angle C. We cross multiply and then we divide by 7. So we have 8 times the sine of angle C divided by 7 that we can clickety-clack to our calculator. So go ahead and clickety-clack to the calculator. 8 sine of 50, close the parenthesis out, divided by 7. Make sure you close the parenthesis out. Because if not, you may divide 50 by 7. We want the sine of 50 divided by 7. So make sure you close your parenthesis out with a 50 and divide by 7. And what you're going to come up with is hopefully a decimal. Okay? Now, if we look at what we're working with here, we have the sine of angle C is equal to this decimal over there. We want to solve for angle C. What that decimal is the sine of angle C. So to solve for angle C, what would we have to do to get rid of your sine? Inverse sine. So you take your inverse sine of your answer. So you go inverse sine and then hit your second button again and hit your negative sign at the bottom. That pulls your answer down from the previous line. Once again, KYC. Taking the inverse sign, not the sine, the inverse sign. So you have second sine, second negative sign. And Trump, what do you get for the measure of angle C? 61.1. So we get the measure of angle C to be 61.1 degrees. So if angle B is 50, angle C is 61.1. Can we solve for angle A now? Yeah, because the triangles have to add up to 180 degrees. So solve for angle A. 68.9 degrees. Because all these angles have to add up to 180 degrees. So we have 68.9 degrees. So now I know angle A. I can use my law of sines once again. Sine of angle A, 68.9 divided by little a, we don't know it, is equal to the sine. I would go back to 50 degrees just in case we move something up, over the value of 7. So we can now solve for little a. Go ahead and solve. Check your heads with somebody around you. Zach, what do you get for little a?
8.5.
8.5. Yes, no, maybe so? 8.5. Now, if we take a look, once again, we can check our triangle by making sure the biggest side is across from the biggest angle, smallest side across from the smallest angle. Our smallest angle is 50. Small side 7. They're opposite each other. Our biggest angle 68.9. Biggest side 8.5. So we have opposites that are good. Okay. And anatomically, if I just look at the triangle, it sort of looks like, yeah, that looks like a good triangle. We have 50 degrees, 61, 68.9. You know, that looks like a triangle that would work. Which is correct. We did everything correctly here. But if we take a look at our given information, we have little b is 7, we have little c is 8, and we have angle b is 50 degrees. If we look at that information, this is the triangle that we have up top. If I would put a hinge up at A and slide little b over to here, making an isosceles triangle here, two sides that are congruent. Okay, two sides congruent isosceles triangle. We can come up with another scenario for the conditions that we are given. Where little big B is still 50 degrees. Little b is still 7. It's not here anymore. It's hinged over to here. And we didn't do anything with little c. So what we have is we have a second possibility or second scenario that we can do with the given information. Okay, it's the same conditions as what we had up top, but now we have a different look to the triangle. The question is, how do I find my other values? What we did up here wasn't exactly correct. Okay, we used our law of sines, we did this, we solved, we came down to values, we said some of the triangles have that, angles have that, under 80 degrees. So we did everything correct. But how can we come up with that second solution? Well, if we look at the process, we set up our law of sines. We proved that yesterday is true, so we're good with that. Okay, we filled in values, 58 and 7. That's correct. We cross-multiplied and we divided. That is correct. Okay, so that whole process that we did there is exactly correct. But if we take a look at the next scenario here, we have the sine of an angle is equal to a decimal. And to solve this problem, we took the inverse sine of both sides. Well, we've solved a bunch of equations in the last chapter or last section that dealt with inverse sine, inverse cosine. We dealt with solving problems that dealt with principal values, and we worked with the idea of the inverse sine. Well, we took the inverse sine of a decimal. We came down to 61.1 degrees, which we call this, because we got it out of our calculator, the principal value. But when you take your inverse sine, we get our calculator principal value, but we can come up with a second solution, which is its what? Supplement. So we had to deal with the supplement. So the measure of angle C could be 61.1 degrees, or the measure of angle C could be the supplement to 61.1. Well, what's the supplement to 61.1? What angle do we have to add to 61.1 to get 180 degrees? How do we get? 118.9. So the measure of angle C could also equal 118.9 degrees, which if I take a look, we've made this an obtuse angle. We have 118.9 degrees, which means the measure of angle A would have to equal what then? Well, this is 118.9, this is 50. What are we left with for angle A? $11.1. Because all of our angles have to add up to 180 degrees. And now we can sit here and go through the law of sines a second time, where we have the sine of our 50 degrees divided by 7, b over little b, is equal to the sine of 11.1 divided by little a. So I could do a second law of sines equation or proportion to be able to solve for little a. What now do we come up with for little a? Rachel, what do you get? Floyd? 1.76. So if we now look at our triangle, our biggest angle is 118.9. Our biggest side is now 8. Our smallest angle is 11.1. Our smallest side is 1.76. Middle. So what we have here is we have a second scenario that will work. What you have to watch out for is when you use your law of sines to find the measure of an angle. You have to worry about two possibilities. Now, when you were in geometry, you went through proving triangles congruent. Okay, you did 2-column proofs and you proved triangles congruent. The first way of proving triangles congruent was the side postulate, which stated to you that 3 sides of one triangle congruent to 3 sides of a second triangle, then the 2 triangles were congruent. You had the side angle side postulate, which said if 2 sides of one triangle and the included angle of one triangle are congruent to 2 sides and the included angle of a second triangle, then the 2 triangles were going to be congruent. You had the angle side angle postulate that said if 2 angles and the included side of one triangle were congruent to 2 angles and the included side of a second triangle, then the 2 triangles were congruent. You also had the angle side postulate that said if 2 angles and the non-included side, yes, pass it. Your phone here. The 2 angles and the non-included side of one triangle are congruent to 2 angles and the non-included side of a second triangle, then the 2 triangles were congruent. And you went through those proving triangles congruent. You had triangles there, and you had to state which one was true. But of course, you sit there and you ponder those thoughts, and I would probably tend to think maybe one of your fellow students said, raised a hand and said, well, yeah, side, side angle, sides, angle, side, angle, angle, side. Where's the angle, side postulate? Where's the angle, side postulate? You have all the other ones there, but you don't have the angle, side postulate. Where is that? Why does that not work? Well, when you're proving triangles are congruent, that means you're going to be able to put one right on top of the other, and you only see one triangle. Put one triangle on top of a second triangle, and then you only see one triangle. They are identical matchups. If we take a look at our two triangles here, we know a side, and an angle. This side angle of this triangle are congruent to side angle of this triangle. I cannot put this triangle on top of that triangle and only see one triangle. I would see two separate triangles. So here is the situation where why the angle side postulate doesn't work. Now, I always call this the Gregory corollary, but corollary is an offshoot of the actual postulates. That would work if the angle was obtuse. If the angle was obtuse, then you would have an angle side postulate. But the angle's acute, you may not have congruency. But if the angle was obtuse, then it would work. Then you would have congruent triangles. But if it's not obtuse, then you're not guaranteed that you're going to have congruency there. So the reason why you don't have that postulate is because of what we just went through right there. Okay, we don't have congruency. We have two sides and one angle not included in one triangle, congruent to two sides and not included angle of the second triangle. The two triangles are not congruent. Questions? It's just more law of sines and cosines. Now, what we have now is some problems to do on page 239. You have 3 to 27 multiples of 3. What they say to do is to solve the triangle for the unknown values. They give you 3 values. What you have to do is find the rest of those values. You have to find the rest of the values here. So they'll give you 3, you find the other 3. You can use law of sines, law of cosines, whatever you want to do. They also give you them in degrees and minutes rather than degrees and decimals. If you're given things in minutes for the measure, you remember how to change that into a decimal. You remember how to change it into a decimal? Divide by 60. So in your calculator, you can go 27 plus 40 divided by 60. That will change it into a decimal. The odds, which are 3, 9, 15, 21. The odd ones and 27. Calculate the area. Also, that's not in the instructions, but it's given to you as solutions. One last thing up here is when you're trying to find the measures of angles, if you're given 3 sides, If you're given three sides, you have to find the three angles. You have to find the angles given three sides. You're going to have to use law of cosines to find the measure of the angles. Now, my suggestion to you is look at the biggest side, find the angle opposite that first. Because the law of cosines is going to give you one solution. It will give you one solution. Okay? You don't have to worry about a supplementary angle or anything like that. You have one solution. If you pick the largest side, how many obtuse angles can you have in a triangle? One. Okay, you can only have one. You can't have more than one obtuse angle because that's more two angles that were greater than 90, which means you have over 180 degrees. So you can only have one obtuse angle. And that obtuse angle has to be across from the biggest side. So the biggest side has to be opposite the biggest angle. If angle C is not obtuse, angle B and A is not going to be obtuse. So then you can use your law of sines to be able to get your angles out of that, which is a little bit easier to manipulate. Trying to make it easier for you. But you know, that's what I do. That's my suggestion for you also. Find the angle that's across from the biggest side first, and then use your law of sines to find the rest of the angles. Okay? Questions you have? You have about 7-8 minutes here within the class. Should be able to get a couple done here. Get 3 or 6 done here within the class. Monday we'll come in. We'll have a worksheet that will combine what we've done the last few days. Tuesday will be a review day. Wednesday will be a quiz over this material. We're quickly sliding to the end here, folks. Quickly sliding to the end.